All right, thank you all for joining us again for our fifth presentation of the day. Our presenter will be Geoffrey Grimmett. He'll be introduced by one of his project mentors, Dr. Diana Felton. Dr. Felton received her MD at the University of California at Davis School of Medicine in 2006. She is currently the state toxicologist at the Hawaii State Department of Health's Hazard Evaluation and Emergency Response Office. At the HERE office, she works with many state and community partners on issues such as childhood lead poisoning prevention, safe fish consumption, air pollution risks, pesticides, and other environmental health hazards. Fantastic work, we need it. And so without further ado, I'd like to welcome Diana Felton, Dr. Felton, to introduce Geoffrey.
Hi, everybody. Thanks so much for having me today. It is such a pleasure to be able to introduce Geoffrey today. He spent his internship with us last summer as part of the Hawaii Childhood Lead Poisoning Prevention Program, which we affectionately refer to as HICLIP. And HICLIP is a CDC-funded program that is run through the Department of Health through both the Children with Special Health Needs branch and my office, the Hazard Evaluation and Emergency Response Office. So the combination of groups really allows for a really interesting approach to environmental health and prevention of a major environmental health program. So Geoffrey just did an excellent job, which he'll tell you all about, but we were just so pleased to have him. Unfortunately, with COVID restrictions, we didn't get as much one-on-one in-person time as we would have liked, but he just did an amazing job taking a really complex problem and producing incredible evaluation and very informative work that's going to help inform the program for going forward. So without further details, I'll let him explain his wonderful project, but we're just so grateful to both Geoffrey and the program. And I also wanted to take a moment to recognize two other HERE staff members, Casey Ingalls and Kelly Hoffman, who were instrumental in assisting Geoffrey with the project as well. So thank you so much to Lisa and the group, and especially to Geoffrey. Go ahead, Geoffrey.
We can see it, but I can't hear you.
Can you hear me now?
We can hear you now, but we can't see your slides.
Oh yeah, because I stopped sharing, sorry.
Oh, okay.
Yeah. Okay. So again, thank you, Diana, for that great introduction. And aloha, everyone. Thank you for attending my TCBES professional internship presentation, where I'll be discussing the internship that I performed at the Hawaii State Department of Health's Hazard Evaluation and Emergency Response Office. And the title of my talk today is The Contribution of Lead Contamination Sites to Childhood Lead Poisoning in the Hawaiian Islands. However, before I get into the details of my project, I want to just give you a brief outline of what my talk will cover today. First, I'm going to go over the background and purpose of my internship project and my internship agency. Then I'll cover the strategies and methods that I used throughout my internship. Next, I'll present the outcomes of my project, specifically the deliverables that I was able to produce. And finally, I'll discuss how this internship has helped inform my professional path and future. So as you all know, lead can be very detrimental to a child's health, where exposure can lead to a wide array of cognitive and behavioral deficits, such as difficulty paying attention, decreased IQ, and poor academic performance, along with the other effects that are listed in the purple circle shown in this diagram, which, as you can see, also causes a ripple effect that follows a child into their future by affecting their employment prospects, their ability to socialize, and by increasing the likelihood that a child will experience lifelong health problems in general. Which all of this then culminates with costs at the societal level, where unemployment, juvenile justice, and healthcare are all negatively affected. So now comes the question of, how does a child get lead poisoning? And the answer to that question is that a child usually comes into contact with a lead exposure source in their immediate environment, where the majority of exposure in the United States is due to deteriorating lead-based paint on the interior and exterior buildings. And the reason why children are at particular risk of exposure when it comes to lead-based paint is due to them participating in exploratory hand-to-mouth behaviors, which can result in them ingesting lead-contaminated dust and paint chips. Soil may also be a source of exposure due to becoming contaminated by exterior lead-based paint, or it can also become contaminated through the historic use of leaded gasoline, welding, and auto repair. And finally, some other risk factors that are specific to or more common in Hawaii are the smelting of lead fishing weights, the use of certain religious and cultural products, and volcanic emissions creating acidic conditions that cause home water catchment systems to leach lead from roofing and plumbing materials. Okay, so now if a child has come into contact with an exposure source, the main indicator of whether a child has lead poisoning is a child's blood lead level, where a blood lead level that is greater than or equal to 5 micrograms per deciliter means that a child has lead poisoning. Though luckily, as time has gone on, we've seen blood lead levels continuously decrease with the introduction of policy aimed at mitigating and preventing lead poisoning, which, as you can see in this figure, starts all the way back with the Lead-Based Paint Poisoning Prevention Act of 1971 and goes all the way up to the lead, dust, and soil hazard standards that were established in 2001. So overall, this observed decrease has been a huge public and environmental health success. However, in recent years, there's been a slight rise in the 95th percentile of blood lead levels for children aged 1 to 5. This rise in blood lead levels has also been seen in Hawaii, where elevated blood lead levels have ranged from 0.8 to 1.4% of the total number of children tested for the years of 2013 to 2019, which you can see in the bottom row of this table, which also presents another problem. Testing rates in Hawaii are very low, where less than 16% of children were tested in the years of 2017 and 2018. So there's a decent possibility that some cases may have gone undocumented. All of this then leads us to the purpose of my internship, which was to aid in the monitoring and the prevention of childhood lead poisoning by assessing how environmental factors, specifically lead-contaminated sites, may be contributing to childhood lead exposure in Hawaii. And I performed this internship at the Hawaii State Department of Health's Hazard Evaluation and Emergency Response Office, whose mission statement is to protect health and the environment by providing leadership, support, and partnership in preventing, planning for, responding to, and enforcing laws relating to releases or threats of releases of hazardous substances to the environment. The HERE office fulfills this mission statement by documenting blood lead test results, following up with a child's physician in order to coordinate treatment, providing lead site investigations at a child's residence to identify the source of exposure, and by providing informational guides to concerned parents. Finally, this internship also allowed me to collaborate with the Hawaii Childhood Lead Poisoning Prevention Program, which is a state-based program whose goals are to increase identification of children with lead poisoning and to coordinate surveillance, clinical treatment, and environmental services. Okay, so now let's get into how I tackled this issue with my project. So my approach basically consisted of 5 overall steps, where the first step was to obtain the residential addresses of children who received a blood lead test between the years of 2015 and 2019 from the Hawaii Electronic Disease Surveillance System. Next, I used GIS to map residential addresses with their corresponding blood lead level. Then I pulled environmental pollution data from the state's IHEAR and Access databases. I followed this up by then creating a layer of IHEAR and Access environmental exposure sites in GIS. And finally, I assessed how these environmental factors may be contributing to childhood lead exposure in Hawaii. Okay, so now we're going to get into more of the specifics of each of those steps. So as I mentioned in the previous slide, blood lead test results that occurred between the years of 2015 and 2019 were chosen for mapping and analysis. This initially consisted of about 81,204 cases. Test results that were not from Hawaii, did not have a residential address recorded, possessed an incomplete address, or only had a medical provider's address were then removed, which resulted in 41,436 cases being left for mapping and analysis. Test results were pared down again after the removal of cases that only contained a post office box as an address. And the reason why post office boxes were removed was due to prior studies which concerned environmental effects on blood lead levels, stating that exact locations were better for statistical analysis rather than PO boxes. And this was due to exact locations being more representative of a child's immediate environment. So after this, test results were then filtered to only include children less than 6 years of age, which left 28,372 cases for mapping and analysis. These remaining test results were then geocoded to latitude and longitude coordinates using the United States Census Bureau's geocoding tool. So when it came to the environmental exposure sites that I mentioned before, these sites were divided into 3 categories: confirmed sites, potential sites, and well sites. And 2 important tools that I used to identify those sites are the state's IHEAR and Access databases, where IHEAR is a map-based database that catalogs known sites of environmental contamination across Hawaii, which would include public, commercial, and private locations. It's managed by the HEAR office and contains geographic data, history of remediation work, and other pertinent documents. Similarly, the Access database also catalogs similar information. However, it's an older database that's mainly for internal use. And the main reason why I use it was that it contains some sites that have yet to be transferred over to the IHEAR system. So going back to the sites, the first category of sites, the confirmed sites, were identified using the IHEAR and Access databases. And the criteria that I used to label a site as a confirmed site as opposed to a potential site included whether the site was suspected to have some form of lead contamination based on historical use, and the site having analytical results that confirmed lead was present at the site with concentration values greater than or equal to the Department of Health's environmental action level of 200 parts per million for lead in soil. Also, you can see an example of a confirmed site on this slide. This is Factory Street, which is located in Kalihi over here on Oahu. And Factory Street is probably considered the most famous lead contaminated site in Hawaii. And this is just due to the very high lead concentration values that were present at the site. They go up to about 121,000 ppm. And then also just the long journey that it took to get this site cleaned up. It took about 27 years for abatement to have occurred and to just be finished, which that took so long mainly due to just issues over jurisdiction over the site. Potential sites were also identified using the Hawaii State Department of Health's IHEAR and Access databases. However, some bridge and airport sites were identified using the Historic Hawaii Foundation's 2013 bridge inventory and the Hawaii Department of Transportation's list of abandoned and forgotten airports located on the HDOT website. And the criteria that I used to label a site as a potential site as opposed to a confirmed site was whether the site in question was suspected to have some form of lead contamination based on historical use, but did not have confirmatory lab results that showed lead contamination at or above the Department of Health's environmental action level of 200 parts per million for lead in soil. So onto the final category site, which were the well sites. So initially, we were just going to compare elevated blood lead levels with confirmed and potential lead sites. However, Diana came across an article in PNAS that found that children in North Carolina that relied on private wells for drinking water had a 25% chance increase in odds of having an elevated blood lead level, as opposed to those who got their drinking water from sources that are regulated under the Safe Drinking Water Act. And the suspected cause of this increase was likely due to household plumbing and well components corroding. So given that there are a multitude of homes across the islands that rely on wells as a source of drinking water, we decided to add these sites to my map into my analysis. These well sites were then identified using a GIS layer provided by the Department of Land and Natural Resources Commission on Water Resource Management, which initially included 5,244 wells. But since the study was only concerned with wells used for domestic drinking purposes, wells that did not fit this criterion were not included in mapping or analysis, which resulted in 899 wells being eligible. And now for the final step, we used the compiled data to make two maps, one that contained elevated blood lead levels in site locations, and one that contained elevated blood lead level rates for census tracts and the location of sites within those tracts. Both of these data sets were then analyzed using a multiple linear regression model, which, if you're unfamiliar with, is a statistical model that is used to estimate the relationship between two or more explanatory variables and one response variable. So for the first map, we use this type of model to determine whether there is a significant relationship at the state and county level between blood lead levels and distance from nearest site and lead concentration value at the nearest site. And for the second map, we determine whether there is a significant relationship between elevated blood lead level rates for census tracts and their number of sites within those tracts at both the state and county level. Okay, so moving on to the outcomes of that mapping and analysis. So here's a statewide view of the first map that contains elevated blood lead levels in site locations, where you can see elevated blood lead levels are represented with an orange dot on the map, where increasing size of the orange dot corresponds to increasing elevated blood lead level values. Confirmed sites are then represented with a black dot on the map, where increasing size of the black dot corresponds to increasing lead concentration values at the confirmed sites. Then potential sites are represented with pink dots, and finally, well sites are represented with blue dots. Also, before I move on, I should also mention that the orange dots that you see on the map, or the elevated blood lead levels, have undergone a process called jittering, which basically means that I added some random noise to those locations. And the reason why I did this for this presentation was to keep the protected health information and other private information of those patients confidential. So the multiple linear regression model at the state level showed a statistically significant relationship between distance from nearest potential site, where the median blood lead level increased as distance between nearest potential site doubled, which, as you can guess, was odd to us since we expected the opposite to happen. So one possible reason that I thought of to explain this occurrence was just the possibility of lead being absent altogether when it came to some of these potential sites. And again, this was just due to a lack of analytical data on those sites. Finally, the multiple linear regression model at the state level also found another statistically significant relationship between blood lead levels and lead concentration value, where median blood lead levels increased by 0.27% as the lead concentration value doubled. Moving on to the county level, the multiple linear regression model for Honolulu County yielded a statistically significant relationship for distance from nearest confirmed site, where median blood lead levels decreased by 1.32% as distance from confirmed site doubled. There is also a significant relationship between blood lead levels and distance from nearest potential site, where median blood lead levels increased by 0.88% as distance from potential site doubled. And finally, there is a statistically significant relationship between blood lead levels and lead concentration value, where median blood lead levels increased by 0.38% as the lead concentration value doubled. For Hawaii County, the multiple linear regression model yielded a significant relationship between blood lead levels and lead concentration value, where median blood lead levels increased by 2.2% as the lead concentration value doubled. Next, the model for Maui County showed no statistically significant relationships between any of the variables. And Kauai County would show similar results with no significant relationships found between any of the variables. Now, moving on to the second map, which shows elevated blood lead level rates per census tract along with site locations. So as you can see, confirmed sites, potential sites, and well sites are represented in the same way as they were with the first map. However, increasing elevated blood level rates are represented with increasingly darker shades of color. So as you can see, it goes from beige to dark red. So the statewide results show a statistically significant relationship between elevated blood level rates and number of well sites within a census tract. For median elevated blood level rates increased by 27.59% as the number of well sites doubled. Moving on to the county level, I saw no significant relationships between any of the variables. Oh, sorry, that was for Honolulu County. Next, for Hawaii County, the multiple linear regression model did not yield any significant relationships between any of the variables. Maui County would continue this trend with no significant relationships being found between any of the variables. And finally, Kauai County also did not yield any significant relationships between any of the variables. So to summarize, overall, our results did not demonstrate a relationship of elevated blood lead levels with residing closer to the confirmed or potential lead contaminated sites that were identified using the IHEAR and ACCESS databases. This supports the idea that most childhood exposures to lead in Hawaii are occurring from lead contamination in and around the home. Also, when it came to elevated blood lead level rates within census tracts, we found that there was a relationship between elevated blood lead level rates and the number of well sites within a tract. This finding is of interest as drinking water is rarely considered a likely source of lead exposure in Hawaii and will require further investigation just due to possible confounding variables, especially since this relationship was not found at the county level. Okay, so now I'm just going to go over some limitations that I experienced during this project. So one limitation that I experienced during the study was the limited quantity of test results due to Hawaii not currently performing universal testing when it comes to blood lead tests. Also, since children are tested for lead only if they screen in for being at risk, the children getting blood tests for lead have a higher pretest probability of having an elevated blood lead level. Therefore, the dataset does not represent all children in Hawaii. Additional limitations of the available data include test results with incomplete address information, results only having PO boxes or healthcare provider addresses, and the fact that not all eligible test results were available to be geocoded. These limitations resulted in there only being 28,372 test results that were available for mapping and analysis. Another possible limitation has to do with our choice of using the largest test result available for cases that had multiple test results. And this was regardless if the test result was from a venous or a capillary blood lead test. And the potential issue with this decision is that there's a significant rate of false positives false positive results from capillary lead tests, creating a possibility that we included false positives in my analysis. That I included false positives in my analysis. And one final limitation was the search limitations for both the IHEAR and ACCESS databases, where it's possible that some sites may have been excluded from the analysis due to neither system possessing the functionality to search by contaminant or by substance. So some ideas that I thought of that could be used to expand upon this project in the future were to include the lead concentration values for private domestic wells in future analyses, and to include housing information such as age of housing in order to assess its effect on both blood lead level values and elevated blood lead level rates per census tract. Okay, so now moving on to more general outcomes. So one of the goals of TCBES professional internship program is for the intern to participate in meaningful and challenging work. And I feel like this is especially true for my internship, since having the opportunity to accomplish work that will help aid in childhood lead poisoning prevention in Hawaii has made this internship just both meaningful to myself and to the community as a whole. And also, since lead has been known to negatively affect both animals and vegetation by inhibiting an animal's ability to synthesize red blood cells and by stunning plant growth, this work will also be incredibly significant to the environment, since the compiling of this data could lead to future abatement efforts that could help mitigate lead poisoning incidents for those organisms. The internship also constantly provided new and exciting challenges, such as learning GIS, which I had never even used, let alone seen before. Putting the skills that I just learned, putting the RStudio skills that I just learned in my quantitative ecology class to the test, and the process of compiling all of my work in order to present it at the end of my internship to both the HERE office and to the Hawaii Club team was just a satisfying and positive experience. During my internship, I was also given some auxiliary tasks, which will have a huge benefit to the HERE office and to Hawaii CLIP. One of these tasks was the creation of a high-risk map based off of census data, such as sociodemographic and housing risk factors, which allowed us to identify areas where children may be at highest risk for lead exposure. Another benefit provided by this map was the ability for the Hawaii CLIP team to compare it to a previous high-risk map that they had made, which was more so based off of zip codes, where this comparison will potentially allow the HERE office and the Hawaii CLIP team to construct a more comprehensive high-risk system. One other event that I was also given a chance to participate in was a lead site investigation, where we took soil, paint, and dust samples at a residence in order to identify possible sources of lead exposure. And this was for a child who had tested for an elevated blood lead level. And this experience was just really cool because it allowed me to see more so the direct effects of both my work and the HERE office's work and trying to prevent like this child from, being exposed to this lead source. Additionally, another goal of the TCBES professional internship program is for the intern to become fully integrated into their agency, where they're comfortable with the culture of the agency and their policies. And due to the welcoming demeanor and tutelage of my mentors, I was able to seamlessly be integrated into my agency, where I feel the results of this easy transition can be seen in my work, where I was able to collaborate with a multitude of my colleagues, which undoubtedly benefited the project as a whole. And this was just due to having like a diverse set of voices that provided me with needed advice, critique, and ideas that helped me make this project as comprehensive as possible. So to conclude, my TCBS journey has been incredibly invaluable to me in my future endeavors. The program has been very accommodating and supportive of me when it's come to my interest in environmental health and epidemiology. My professors and colleagues have also taught me so much about the conservation and environmental science fields in general, which has just expanded my knowledge and awareness of fields that I had no prior experience in. My colleagues have also been really important to me since they're my biggest source of inspiration and have been a great support system throughout my entire time in this program. And of course, my internship was also an incredibly fulfilling experience that allowed me to gain a deeper insight into the environmental health field, while also being able to participate in work that will help make a difference in Hawaii. And I'm particularly grateful to my mentors who were extremely kind, informative, and supportive of me and my goals. they made a constant effort to make sure that I had an opportunity to be involved with as many different facets of their work as possible. And I'm really hopeful that we'll be able to work again with each other in the future and possibly expand upon this project. So overall, my time in this program has been really special and will continue to be influential in my professional path and future development. And finally, I'd like to again thank my mentors, Dr. Diana Felton, Casey Ingalls, Kelly Hoffman, and the entire Hawaii State Department of Health's Hazard Evaluation and Emergency Response Office, along with the Hawaii Childhood Lead Poisoning Prevention Program, for providing this internship opportunity to me and for their guidance and support throughout this entire process. I'd also like to thank my advisor, Lisa Canali, for her assistance in obtaining this internship and for her constant support over the course of these past 2 years in the TCBES program. And finally, I would like to thank the University of Hawaii at Hilo, the TCBES graduate program, and my cohort for making these past 2 years of graduate school a very special and fulfilling experience. And that was my presentation. Mahalo to you all. Thank you. If you have any questions that I'm not able to get to, my contact information is at the top right of the slide.
All right. Thank you so much, Geoffrey. That was very informative. Greatly appreciate your work on this and your willingness just to jump in and do a bunch of self-teaching. Your maps looked great. So I'd like to open up the floor for questions. So if you are brave, please just go ahead and unmute yourself, or you can place it into the chat. And while we're waiting for that typing to happen, I have a question for you, and that's related to that deep data dive that you did to into those two databases. And you know, I'm wondering, now that you have seen like how much data needs to be cleaned up, and you've recognized what fields maybe were missing, like what suggestions would you have to the HERA office in moving forward in terms of their data collections?
Well, I know that currently, or they're in the HERA office was in the process of updating those databases to where they would be more, they would have the ability to search by contaminant or by substance. So I think that's a huge step, because that would really cut down the time to, search through all those documents. But also, I think for the most part, all that data was pretty well organized and kept together. The only thing that how should I say, that was a little bit hard was sometimes it wouldn't have like coordinates or anything, or like an actual location. So I would have to, do some digging, but that was never really a huge issue. It was all good.
I have a question.
Yes.
Since you didn't find that the distance was really important, but and you think most lead exposure is coming from the home, what would be like the next steps to try to like pinpoint what are some of the factors? Would it be like looking at household income, or some kind of neighborhood statistics, or what kind of things would you want to know to kind of pinpoint what are the reasons, age of the houses in the area? What are the things you want to kind of learn next? Would you suggest?
So I think age of housing is really important, because again, like the older the house, the more likely it is to have lead-based paint. I also think socio-demographic like information, like you said, as like income, whether that person is making, below the poverty line or stuff like that. Also, I guess just age of the tenants too, like could also help out, just because like someone who's younger is probably going to, I guess, more so have the funds to only have the funds to maybe rent, or probably just rent, like a place that may be contaminated with lead.
Right, thank you. So Becky, is there anything happening on the YouTube channel? Nope, no questions through YouTube. All right, so I'm going to give you all a couple more minutes to think of a question, and feel free just to go ahead and unmute yourself.
Hi, Geoffrey. My name's Lenore. I have a quick question for you regarding the last map that you created about, maybe you could actually flip black in the slides. So it was that one there, the high risk map.
Yes.
Can you talk about how you created that and what social vulnerability index means?
So the social vulnerability index is like a metric used by the CDC that takes a bunch of risk factors, such as, again, it's like sociodemographic information. So it's income, it has housing risk factors like age of housing, it has minority status, it has level of education, it has all those things. Um, and what one of my mentors did, Casey, she was the one who calculated the weight one value that you see here, which is what we use to basically symbolize risk, or represent risk, or increasing risk. So I basically just took that data and then made this map. And then the main things that I did was just noting where differences were in this map and then the previous map that Hawaii Clip already had. So like some of the differences were, like with this map, it had North Kona and the Hamakua area as high risk, whereas the previous one did not. I believe it was not considered high risk. So it was just pointing out those types of differences, and then I presented that to the Hawaii Clip team during their June coalition meeting.
Awesome. So just a follow-up question then from that. Did you plot the actual cases over the top of this map?
No, I did not. This was just seeing like where new high risk areas were and where they had previously been before, which is what the black dots symbolize on here, which were the previous high risk zip codes from the other map.
Okay, and then just I'm sorry to keep asking so many questions, but
No.
the weight numbers there, can you help me understand what they mean, what the differences are? I mean, numerically, I can understand the difference, but if you could just talk a little bit about, you know, these decimal points don't really mean anything to me. So if you could help explain that, that would be helpful.
Okay, so the reason why it's spaced out so much was just to, I guess, be as granular as possible, just so that we can just have a, let's see, sorry, I'm trying to think what the word is, just to break it down as much as possible to see, like, where, just to highlight what the highest risk areas are. So the divisions that you see here are, I don't want to say arbitrary, but it was more so spaced out like that, again, just to have that like stepping scale, so we could have some differentiation and to see what areas should be, narrowed down so that they can be prioritized, for possible, lead poisoning prevention efforts like abatements, or giving out the questionnaire to children in that area, which the questionnaire is used to target lead tests in Hawaii. That's how we do that.
I see. So still a follow-up question. So let's just use Big Island for an example. Is it at a
Mhm.
higher risk because of older housing stock, or is it a combination of things like socioeconomic status? And I mean, can you pull that out from this map, or are we just looking, when we're looking at it all together like that, it's difficult to know why there are these differences? Do you have any insight into that?
Um, I'm I'm not. Mm, I would agree that it's probably going to be a bit harder with this current map as to pull that specific information out. But um, if I had to make just a guess or to give like my opinion, I would imagine it has to do more of just older housing. But again,
Okay.
like I can't be 1,000% sure about that.
Right. Sorry to keep putting you on the spot. I just have lots of questions, but
Oh
I
no,
saw
it's
Diana just posted the vulnerability index from the CDC, which is really helpful. So I'll take a look at that. Thank you so much, Geoffrey.
thank you for your questions.
And I can just chime in a little bit about the SVI. So the CDC's SVI, which is what Geoffrey used for this, and Casey, is sort of designed to try to get a picture of communities that are at higher risk from external stressors from a lot of different things. So in the past, a lot of look at environmental disparities or health disparities has all been based on income, and the SVI is designed to look at more than just income. And so there's a whole list of criteria. And so what was so useful about doing this project was in the past, our high risk zip codes, which are represented by the black dots that High Clip has used in the past, are really based mostly on income and age of housing and sort of lower economic neighborhoods. And we wanted to get a broader look at other things that may be impacting potential exposure to lead and childhood lead poisoning, which are some of the things in the CDC SVI. So this is just one way to look at it. And it was interesting, as Geoffrey found, to find out that it didn't line up perfectly. So sort of spurs us on to do more work to look for other contributors and other things that may be affecting kids' possible exposure to lead and risk. So hope that helps clarify.
It does. Thank you, Diana.